What if everything you thought you knew about reality was just the tip of the iceberg? What if hidden beneath the surface of our everyday world lies a universe, or perhaps countless universes operating by rules so strange they defy everything we've ever been taught? Welcome to a journey that will stretch the limits of your imagination and challenge the very fabric of what you believe to be real. Today, we're diving into 30 mind-bending theories about the universe's quantum universes, ideas so profound they might just change the way you see existence itself. Quantum mechanics, the science of the incredibly small, has already turned our understanding of reality upside down. Particles that exist in two places at once, objects that change when we observe them, and connections that span across the cosmos faster than the speed of light. These are just a few of the bizarre phenomena that quantum physics has revealed. But what if these strange behaviors are clues to something even bigger? What if our universe is just one thread in a vast, intricate tapestry of parallel realities, each one shaped by the tiniest quantum decisions? In this video, we'll explore theories that range from the mind-blowing to the downright unsettling. From the idea that every choice you make spawns an entirely new universe, to the possibility that our reality might be nothing more than a hologram projected from the edge of space, these concepts will take you on a journey through the wildest frontiers of science and philosophy. So buckle up and keep watching, because by the end of this video, you might just find yourself questioning not just the universe, but your very place within it. Let's begin. Now, let's step into the first theory, one that might make you question every decision you've ever made. This is the many worlds interpretation, a mind-bending idea that suggests every quantum decision doesn't just lead to one outcome, it spawns an entirely new universe. Imagine this: every time you make a choice, no matter how small, the universe splits into multiple versions, each one representing a different path. In one universe, you might have chosen to stay home today, while in another, you're off on an adventure. This isn't science fiction, it's a serious scientific theory that challenges our understanding of reality itself. The many worlds interpretation was first proposed in the 1950s by physicist Hugh Everett, who was trying to make sense of the strange behavior of quantum particles. In the quantum world, particles exist in a state of superposition, meaning they can be in multiple states at once until they're observed. Everett's radical idea was that every possible outcome of a quantum event actually happens, but in separate, branching universes. So, instead of a single timeline, there's an infinite multiverse, with every possible version of reality playing out simultaneously. But what does this mean for us? For starters, it raises fascinating questions about free will. If every decision creates a new universe, are we truly making choices, or are all possibilities already playing out somewhere? It also opens the door to the idea of alternate realities, worlds where history took a different turn, where dinosaurs never went extinct, or where you became a rock star instead of watching this video. While the many worlds interpretation is still debated, it's a powerful reminder of just how strange and vast the universe or universes might be. And as we'll see next, this is just the beginning of the quantum rabbit hole. Now, let's shift our focus to another cornerstone of quantum mechanics, the Copenhagen interpretation. Unlike the many worlds interpretation, which suggests an infinite branching of universes, this theory takes a different approach to explain the strange behavior of quantum particles. At its core, the Copenhagen interpretation proposes that particles exist in a state of superposition, meaning they can be in multiple states at once until they are observed. It's only when we measure or observe them that they collapse into a single, definite state. This idea was developed in the 1920s by pioneers like Niels Bohr and Werner Heisenberg, who were trying to make sense of the puzzling results coming out of early quantum experiments. Think of it like this: imagine a coin spinning in the air. While it's spinning, it's neither heads nor tails. It's in a superposition of both possibilities. But the moment you catch it and look, it lands on one side. In the quantum world, particles behave similarly, existing in all possible states until an observation forces them to choose one. But here's where things get even more intriguing. The Copenhagen interpretation suggests that the act of observation itself plays a crucial role in shaping reality. This raises profound philosophical questions. Does reality only exist because we observe it, or does observation simply reveal what was already there? Some argue that this interpretation places the observer at the center of the universe, blurring the line between the physical world and our perception of it. This theory also introduces the concept of wave function collapse, which describes how a particle's probability wave, a mathematical representation of its possible states, collapses into a single outcome upon measurement. While this idea has been incredibly successful in predicting experimental results, it's not without its critics. Some physicists find it unsatisfying because it doesn't explain why observation causes collapse or what exactly constitutes an observer. Despite these debates, the Copenhagen interpretation remains one of the most widely taught and accepted views in quantum mechanics. It challenges us to rethink not just the nature of particles, but the very nature of reality itself. And as we'll see next, the quantum world has even more surprises in store for us. Now, let's dive into one of the most mind-bending phenomena in quantum mechanics: quantum entanglement. Imagine two particles, perhaps photons or electrons, that become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This connection, known as entanglement, defies everything we know about classical physics, where objects are bound by the speed of light and the constraints of space and time. Albert Einstein famously called this phenomenon spooky action at a distance, and he was deeply skeptical of it. Along with his colleagues Boris Podolsky and Nathan Rosen, Einstein argued that quantum mechanics must be incomplete because it seemed to allow for instantaneous communication between particles, which contradicted his theory of relativity. They proposed that there must be some hidden variables, unknown factors, that determine the behavior of these particles, making their connection seem instantaneous when it wasn't. But here's where the story takes a fascinating turn. Decades later, physicist John Bell developed a mathematical framework to test whether hidden variables could explain entanglement. His work led to experiments that ultimately proved Einstein wrong. In the 1980s, physicist Elaine Aspect conducted groundbreaking experiments that showed entangled particles do indeed influence each other instantaneously, even when separated by vast distances. This phenomenon, known as non-locality, has since been confirmed in countless experiments, leaving no doubt that entanglement is a real and fundamental aspect of the quantum world. So, how does this work? When two particles become entangled, they share a single quantum state. Measuring one particle instantly determines the state of the other, regardless of the distance between them. It's as if they're connected by an invisible thread that transcends space and time. This has profound implications for our understanding of reality, suggesting that the universe is far more interconnected than we ever imagined. Quantum entanglement isn't just a theoretical curiosity, it's also the foundation for emerging technologies like quantum computing and quantum cryptography. These fields rely on the unique properties of entangled particles to perform tasks that would be impossible with classical systems. For example, quantum computers use entanglement to process information in parallel, potentially solving complex problems in seconds that would take traditional computers thousands of years. As we continue to explore the mysteries of entanglement, one thing is clear: the quantum world challenges our most basic assumptions about how the universe works. And as we'll see next, this is just the beginning of the strange and wonderful phenomena that quantum mechanics has to offer. Now, let's shift our focus to a theory that turns our understanding of the universe on its head: the holographic principle. This mind-bending idea suggests that everything we perceive as three-dimensional space might actually be a projection from a two-dimensional surface. In other words, the universe could be like a hologram where all the information about the cosmos is encoded on a flat 2D boundary, and what we experience as depth and volume is just an illusion. The roots of this theory lie in the study of black holes. In the 1970s, physicist Jacob Bekenstein discovered that the entropy, or the amount of information contained within a black hole, is proportional to the area of its event horizon, not its volume. This was a groundbreaking insight because it hinted that the information about everything that falls into a black hole isn't lost but is instead encoded on its surface. Later, physicist Leonard Susskind and Nobel laureate Gerard T. Hooft expanded on this idea, proposing that the entire universe might operate in a similar way. They suggested that all the information about the cosmos could be stored on a boundary, much like a hologram stores a 3D image on a 2D surface. But what does this mean for our understanding of reality? If the holographic principle is correct, it implies that the universe we experience is a kind of projection, and the true nature of reality might be far simpler than we imagine. It challenges the very notion of space and time as fundamental constructs, suggesting instead that they emerge from deeper, more abstract principles. This idea has profound implications for physics, as it could provide a way to reconcile quantum mechanics with general relativity, two theories that have long been at odds. The holographic principle also raises fascinating questions about the nature of information. If the universe is a hologram, then information might be the most fundamental building block of reality, more basic than particles or forces. This perspective aligns with other cutting-edge theories like quantum information theory, which we'll explore later in this video. As we continue to unravel the mysteries of the cosmos, the holographic principle reminds us that reality might be far stranger and more interconnected than we ever imagined. And as we'll see next, this is just one of the many ways quantum mechanics challenges our understanding of the universe. Now, let's dive into a theory that takes us even deeper into the fabric of reality: string theory. Imagine if the smallest building blocks of the universe weren't tiny dots like particles, but instead were incredibly small, vibrating strings. These strings, so tiny that they're far beyond our ability to observe directly, could be the fundamental units of everything in existence. According to string theory, the different vibrations of these strings give rise to all the particles and forces we see in the universe, from electrons to photons to gravity itself. One of the most exciting aspects of string theory is its potential to unify two of the most important but seemingly incompatible theories in physics: quantum mechanics and general relativity. Quantum mechanics describes the behavior of the very small, like atoms and particles, while general relativity explains the behavior of the very large, like stars and galaxies. For decades, scientists have struggled to reconcile these two frameworks, but string theory offers a possible solution. By describing all particles and forces as different vibrations of strings, it provides a single, elegant framework that could encompass both quantum mechanics and general relativity. However, string theory isn't without its challenges. One of the biggest hurdles is that it requires extra dimensions beyond the three spatial dimensions and one time dimension we're familiar with. In fact, string theory suggests there could be as many as 10 or even 11 dimensions. These extra dimensions are thought to be curled up or hidden in such a way that we can't perceive them directly, which makes the theory difficult to test experimentally. Additionally, string theory is incredibly complex mathematically, and so far, there's no direct experimental evidence to confirm its predictions. Despite these challenges, string theory remains one of the most promising candidates for a theory of everything, a single framework that explains all the fundamental forces and particles in the universe. It has inspired countless physicists and led to groundbreaking insights, even if its ultimate validity remains unproven. As we continue to explore the mysteries of the cosmos, string theory reminds us that the universe might be far more intricate and interconnected than we ever imagined. And as we move forward, we'll explore another fascinating theory that offers a different perspective on the quantum universe: loop quantum gravity. This theory takes a unique approach to resolving the same fundamental questions, and it's just as mind-bending as string theory. Stay tuned. Now, shifting our focus to another groundbreaking idea, let's explore loop quantum gravity. While string theory imagines the universe as a symphony of vibrating strings, loop quantum gravity takes a completely different approach. Instead of strings, this theory suggests that spacetime itself is made up of tiny, discrete loops. These loops are the building blocks of reality, woven together to create the fabric of the universe. In this framework, spacetime isn't smooth and continuous as we often think of it, but rather granular, like a finely woven tapestry. One of the key motivations behind loop quantum gravity is its attempt to resolve the long-standing conflict between quantum mechanics and general relativity. Quantum mechanics governs the behavior of the very small, while general relativity explains the behavior of the very large, like planets and galaxies. For decades, physicists have struggled to find a way to merge these two theories into a single, unified framework. Loop quantum gravity tackles this challenge by proposing that spacetime itself is quantized, meaning it's made up of tiny, indivisible units. This idea is a radical departure from the smooth, continuous spacetime described by general relativity, but it offers a potential solution to the problem of quantum gravity. In loop quantum gravity, these tiny loops of spacetime form a network, often referred to as a spin network. The connections between these loops determine the geometry of spacetime itself. When you zoom out, this network gives rise to the familiar, smooth spacetime we experience in our everyday lives. But at the smallest scales, spacetime becomes a dynamic, ever-changing structure full of twists and turns. This granularity also has profound implications for the nature of black holes and the Big Bang. For instance, loop quantum gravity suggests that the singularity at the center of a black hole, a point of infinite density, might not exist. Instead, the theory predicts that quantum effects would prevent such singularities from forming, offering a new way to understand these cosmic mysteries. Like string theory, loop quantum gravity is not without its challenges. One of the biggest hurdles is the difficulty of testing its predictions experimentally. The scales at which these quantum effects become significant are far beyond our current technological capabilities. Additionally, the mathematics behind loop quantum gravity is incredibly complex, making it a challenging theory to work with. Despite these obstacles, the theory has gained significant traction among physicists, offering a compelling alternative to string theory in the quest for a unified theory of everything. As we continue our journey through the quantum universe, loop quantum gravity reminds us that there's more than one way to approach the deepest questions in physics. Whether through strings or loops, these theories push the boundaries of our understanding, inviting us to rethink the very nature of reality. And next, we'll explore another intriguing idea, the simulation hypothesis, which takes us into the realm of philosophy and technology, asking whether our universe might be something entirely different than we've ever imagined. Now, let's take a step into a theory that blurs the line between science and philosophy, the simulation hypothesis. This idea suggests that our entire universe, including everything we see, feel, and experience, might actually be an incredibly advanced computer simulation. Think about it. If future civilizations could create simulations so realistic that the beings inside them believe they're real, how could we ever be sure we're not one of them? This isn't just science fiction. It's a serious question that has sparked debates among scientists, philosophers, and tech enthusiasts alike. The roots of this idea go back centuries, with philosophers like René Descartes questioning the nature of reality. But in modern times, the simulation hypothesis gained traction thanks to thinkers like Nick Bostrom, who proposed a compelling argument. He suggested that if a civilization reaches a level of technological sophistication where it can create simulations indistinguishable from reality, it's statistically likely that we're living in one of those simulations rather than the base reality. In other words, the odds might be stacked in favor of us being part of a simulated universe. Technological parallels also lend credibility to this theory. Consider how far we've come in creating virtual worlds. Video games, virtual reality, and artificial intelligence are becoming increasingly lifelike. If this trend continues, it's not hard to imagine a future where simulations are so advanced that they're indistinguishable from the real world. Some argue that this progression could lead to a point where simulated realities outnumber the original one, making it more probable that we're living in a simulation. The simulation hypothesis also ties into the Fermi paradox, which asks, if the universe is so vast and filled with potential for life, why haven't we encountered any signs of extraterrestrial civilizations? One possible answer is that advanced civilizations might choose to create simulations rather than explore the physical universe. If that's the case, it could explain why we haven't found evidence of alien life. They might be too busy running simulations of their own. Of course, this theory isn't without its skeptics. Some argue that the computational power required to simulate an entire universe would be beyond anything we can imagine. Others point out that even if we are in a simulation, it doesn't change the fact that our experiences feel real to us. Whether or not the simulation hypothesis is true, it challenges us to rethink our understanding of reality and our place in the cosmos. As we move forward, this theory invites us to consider the nature of existence itself. Are we living in a simulated universe, or is this the base reality? And if we are in a simulation, what does that mean for the future of humanity? These questions might not have easy answers, but they push us to explore the boundaries of science, philosophy, and technology in ways that are both thrilling and thought-provoking. Next, we'll dive into the anthropic principle, which explores how the universe seems perfectly fine-tuned for life, and what that might tell us about the nature of existence. Now, let's shift our focus to a theory that feels almost tailor-made for us, the anthropic principle. This idea revolves around the observation that the universe appears to be finely tuned for the existence of life. Think about it. If the fundamental constants of nature, like the strength of gravity or the charge of an electron, were even slightly different, life as we know it wouldn't exist. It's as if the universe has been calibrated with precision, raising the question, why does it seem so perfectly suited for us? The anthropic principle comes in two main flavors, the weak version and the strong version. The weak anthropic principle suggests that the conditions we observe in the universe must allow for the existence of observers, us. In other words, we're here because the universe happens to have the right properties to support life. It's a bit like winning the cosmic lottery. If the universe weren't this way, we wouldn't be around to notice. This version doesn't necessarily imply any deeper meaning or design. It simply acknowledges that we're observing a universe compatible with our existence. On the other hand, the strong anthropic principle takes things a step further. It proposes that the universe must have properties that allow life to arise at some point. This version hints at a more purposeful explanation, suggesting that the fine-tuning of the universe isn't just a coincidence. Some interpretations even suggest that the universe might have been designed with life in mind, though this idea ventures into philosophical and even theological territory. But what does this fine-tuning mean for the broader picture? One possibility is the existence of multiple universes, or a multiverse. If there are countless universes, each with different physical constants, it's not surprising that at least one of them would have the right conditions for life. In this view, we just happen to live in the universe where everything aligns perfectly for our existence. It's a bit like finding a needle in a cosmic haystack, except the haystack is infinite. The anthropic principle also ties into some of the other theories we've explored, like the simulation hypothesis and the multiverse. If our universe is one of many, or if it's a simulation, the fine-tuning we observe might be less about chance and more about the nature of reality itself. It's a fascinating intersection of physics, philosophy, and even metaphysics, challenging us to consider whether our existence is a happy accident or part of a larger, more intricate design. As we ponder these ideas, the anthropic principle invites us to reflect on our place in the cosmos. Are we the result of a finely tuned universe, or is there something more at play? Whether you lean toward the weak or strong version, this principle reminds us that the universe is full of mysteries waiting to be unraveled. Next, we'll explore the quantum Zeno effect, a phenomenon that shows how observation can literally freeze time in the quantum world. Now, let's step into a phenomenon that feels like something straight out of science fiction, the quantum Zeno effect. Named after the ancient Greek philosopher Zeno of Elea, who famously proposed paradoxes about motion and change, this effect reveals something astonishing about the quantum world. The act of observation can literally freeze a system in place. Imagine watching a pot of water, and every time you look at it, the water stops boiling. That's the quantum Zeno effect in action, but on a much smaller and stranger scale. At its core, the quantum Zeno effect occurs when a quantum system is continuously observed. In the quantum realm, particles exist in a state of superposition, meaning they can be in multiple states at once until they're measured. But if you keep measuring or observing the system repeatedly, something peculiar happens. The system gets stuck in its current state. It's as if the act of looking at it prevents it from evolving or changing. This isn't just a theoretical idea. It's been experimentally demonstrated in labs, showing that observation has a profound impact on quantum behavior. So, what does this mean for our understanding of time? Well, the quantum Zeno effect suggests that time itself might not flow as smoothly as we think. In the quantum world, time can appear to slow down or even stop under constant observation. This raises fascinating questions about the nature of time and whether it's as fixed and linear as we experience it in our everyday lives. Could time be more fluid, more malleable than we realize? The quantum Zeno effect hints that the answer might be yes, but the implications don't stop there. This effect also ties into the role of consciousness in shaping reality. If observation can freeze a quantum system, does that mean our awareness has a direct influence on the world around us? Some interpretations suggest that consciousness itself might play a role in collapsing quantum superpositions, bringing reality into a definite state. While this idea is still highly debated, it opens up a realm of possibilities about the connection between mind and matter. The quantum Zeno effect also challenges our understanding of change and stability. In the macroscopic world, we take for granted that objects remain stable unless acted upon. But in the quantum realm, stability can be a result of constant observation. This blurs the line between what's real and what's observed, pushing us to rethink the very foundations of reality. As we wrap up this exploration, the quantum Zeno effect leaves us with more questions than answers. How does observation shape the universe? Is time truly as fixed as it seems? And what role does consciousness play in the fabric of reality? These are the kinds of mysteries that keep physicists and philosophers alike awake at night. Next, we'll dive into the pilot wave theory, a fascinating alternative to the traditional Copenhagen interpretation of quantum mechanics. Now, let's shift our focus to a theory that offers a radically different perspective on the quantum world, the pilot wave theory, also known as Bohmian mechanics. Unlike the Copenhagen interpretation, which suggests that particles exist in a haze of probabilities until observed, the pilot wave theory proposes that particles always have definite positions, guided by an invisible force known as the pilot wave. Imagine a surfer riding a wave. The surfer is the particle, and the wave beneath them is the guiding force that determines their path. This theory brings a sense of order to the seemingly chaotic quantum realm. The pilot wave theory was first introduced by Louis de Broglie in the 1920s, but was later developed more fully by David Bohm in the 1950s. It challenges the idea that particles don't have definite properties until measured. Instead, Bohmian mechanics suggests that particles are always real and have precise positions, even if we can't see them directly. The pilot wave, which exists alongside the particle, acts as a kind of cosmic GPS, steering the particle along its trajectory. This means that, in this framework, the randomness we observe in quantum mechanics isn't fundamental, it's just a result of our limited knowledge of the pilot wave's influence. One of the most striking differences between the pilot wave theory and the Copenhagen interpretation is how they handle the role of the observer. In the Copenhagen view, the act of measurement collapses the wave function, forcing a particle to choose a state. But in Bohmian mechanics, the observer doesn't play such a central role. The particle's position is always real, and the pilot wave ensures it follows a deterministic path. This removes some of the philosophical puzzles about observation and reality that the Copenhagen interpretation raises, offering a more intuitive picture of the quantum world. For decades, the pilot wave theory was largely overlooked, dismissed as an outdated or overly complicated alternative to mainstream quantum mechanics. However, in recent years, it has experienced a revival. Modern experiments and theoretical work have shown that Bohmian mechanics can reproduce all the predictions of standard quantum mechanics, while also providing a clearer, more deterministic framework. Some physicists argue that it could even help resolve long-standing issues such as the measurement problem by offering a more complete description of quantum systems. The revival of the pilot wave theory also highlights an important lesson in science. Sometimes, ideas that seem out of step with the mainstream can resurface with new relevance. As we continue to explore the quantum world, theories like Bohmian mechanics remind us that there's still much to discover and that alternative perspectives can shed light on the mysteries of the universe. Next, we'll explore the quantum immortality hypothesis, a mind-bending idea that challenges our understanding of life, death, and the multiverse. Now, let's venture into one of the most thought-provoking ideas in quantum theory, the quantum immortality hypothesis. This theory takes the concept of the multiverse to an entirely new level, suggesting that consciousness might never truly end, even in the face of death. At its core, the quantum immortality hypothesis proposes that in an infinite multiverse, every possible outcome of a quantum event exists in some parallel universe. This means that if there's even the slightest chance of survival in any scenario, your consciousness would continue in a universe where you didn't die. It's a concept that blurs the line between science and philosophy, challenging our understanding of life, death, and existence itself. The idea stems from the many worlds interpretation of quantum mechanics, which we discussed earlier. According to this interpretation, every decision or random event creates a branching of universes, each representing a different outcome. In the context of quantum immortality, if you were to face a life-threatening situation, there would always be at least one universe where you survive. From your perspective, you would only experience the universes where you continue to exist, creating the illusion of immortality. It's a bit like being the protagonist in a never-ending story where death is always just out of reach. But what does this mean for our understanding of life and death? On one hand, the quantum immortality hypothesis offers a fascinating perspective on the resilience of consciousness. It suggests that, in some sense, we might always find a way to live on, even if only in alternate realities. On the other hand, it raises profound philosophical and ethical questions. If consciousness persists indefinitely across universes, does that diminish the value of life in any single reality? And what does it mean for our sense of identity if we're constantly branching into different versions of ourselves? The ethical implications are equally intriguing. If quantum immortality were true, it could challenge our notions of responsibility and consequence. For example, if every action leads to a branching of universes, does that mean we're absolved of the outcomes in the realities we don't experience? Or does it place even greater importance on the choices we make, knowing that every decision could ripple across countless universes? These questions don't have easy answers, but they invite us to think deeply about the nature of existence and our place within it. While the quantum immortality hypothesis remains speculative, it serves as a powerful reminder of how quantum mechanics can push the boundaries of our imagination. It challenges us to consider not just the physical laws of the universe, but also the philosophical and ethical dimensions of our existence. As we continue to explore the mysteries of quantum theory, ideas like this remind us that the universe is far stranger and more wondrous than we often assume. Next, we'll dive into the black hole information paradox, a puzzle that has puzzled physicists for decades and continues to challenge our understanding of the cosmos. Now, let's shift our focus to one of the most perplexing puzzles in modern physics, the black hole information paradox. This mystery strikes at the heart of quantum mechanics and general relativity, two of the most successful theories in science, yet they seem to clash when it comes to black holes. The paradox arises from a simple but profound question: what happens to information when it falls into a black hole? According to quantum mechanics, information can never be destroyed. It's a fundamental principle that underpins everything from particle physics to the behavior of atoms. But black holes, with their immense gravitational pull, appear to break this rule. Once something crosses the event horizon, the point of no return, it's gone forever, or so it seems. The problem became even more puzzling when Stephen Hawking discovered that black holes aren't completely black. They emit radiation, now known as Hawking radiation, which causes them to slowly lose mass and eventually evaporate. But here's the catch: Hawking radiation appears to be random, carrying no information about the matter that fell into the black hole. If the black hole evaporates completely, where does all that information go? This is the essence of the black hole information paradox. It's as if you burned a book and the ashes gave no clue about the words it once contained. Quantum mechanics insists the information must still exist somewhere, but black holes seem to defy this rule. To resolve this paradox, physicists have proposed several intriguing solutions. One of the most prominent ideas is the holographic principle, which suggests that all the information about the matter swallowed by a black hole is encoded on its surface, specifically on the event horizon. Think of it like a cosmic hologram, where a two-dimensional surface contains all the data needed to reconstruct a three-dimensional object. This principle implies that the information isn't lost, it's just stored in a way we don't yet fully understand. Another proposed solution involves Hawking radiation itself. Some theories suggest that the radiation might not be as random as it seems and could carry subtle imprints of the information that fell into the black hole. If true, this would mean the information is slowly leaking back into the universe as the black hole evaporates. The implications of solving this paradox are enormous. It could help us bridge the gap between quantum mechanics and general relativity, two theories that have resisted unification for over a century. It might also deepen our understanding of the nature of space, time, and information itself. But for now, the black hole information paradox remains one of the greatest unsolved mysteries in physics, a testament to how much we still have to learn about the universe. As we continue to explore the mysteries of quantum universes, the black hole information paradox reminds us that even the most well-established theories can be challenged by the cosmos. Next, we'll delve into the quantum multiverse, a concept that builds on the many worlds interpretation and takes us even deeper into the realm of parallel realities. Now, let's take a step beyond the black hole information paradox and venture into a concept that stretches the boundaries of our imagination, the quantum multiverse. Building on the many worlds interpretation we explored earlier, This theory suggests that every quantum event doesn't just create a single outcome but spawns an entirely new universe. Imagine a cosmic tree with infinite branches, each representing a different reality born from every possible quantum decision. This isn't science fiction. It's a serious scientific idea that challenges our understanding of existence itself. At the heart of the quantum multiverse is the idea that every time a particle can go left or right, spin up or down, or exist in a superposition of states, the universe splits. In one branch, the particle goes left, in another, it goes right. This means that every possible outcome of every quantum event actually happens, just in a different universe. The implications are staggering. Somewhere out there, there's a universe where you made a different choice this morning, a universe where dinosaurs never went extinct, or even a universe where the laws of physics are entirely different. But how does this connect to time travel and parallel realities? Well, if every quantum event creates a new universe, then time itself becomes a web of infinite possibilities. Traveling through time wouldn't just mean moving backward or forward in a single timeline. It could mean hopping between these branching realities. Picture this: you go back in time to change a decision, but instead of altering your own past, you simply step into a parallel universe where that decision played out differently. Your original timeline remains untouched, but you've entered a new reality where history unfolds in a new way. This idea also raises fascinating questions about identity and continuity. If there are infinite versions of you across the multiverse, are they all truly you, or are they separate beings with their own experiences and choices? The quantum multiverse doesn't just challenge our understanding of physics, it forces us to rethink what it means to exist. While the quantum multiverse remains a theoretical framework, it offers a compelling way to reconcile the strange behavior of quantum particles with our everyday experience of reality. It suggests that the universe isn't just vast, it's infinite, with every possible outcome playing out somewhere in the cosmic tapestry. As we continue to explore the mysteries of quantum mechanics, the multiverse reminds us that reality might be far more complex and interconnected than we ever imagined. Next, we'll turn our attention to another mind-bending idea: quantum consciousness. Could the strange phenomena of quantum mechanics hold the key to understanding how our minds work? Let's find out. Now, shifting our focus from the vastness of the quantum multiverse, let's zoom in on something much closer to home: our own minds. The quantum consciousness theory proposes that the mysterious nature of consciousness might be deeply tied to the strange world of quantum mechanics. This idea suggests that the brain isn't just a classical computer made of neurons firing in predictable patterns. Instead, it might operate on a quantum level where particles can exist in multiple states at once, and where the act of observation itself could play a role in shaping our thoughts and experiences. One of the most prominent figures behind this theory is Roger Penrose, a renowned physicist and mathematician. Alongside anesthesiologist Stuart Hameroff, Penrose proposed that consciousness arises from quantum processes occurring within tiny structures in the brain called microtubules. These microtubules, found in neurons, might act as quantum computers, processing information in ways that classical physics can't fully explain. According to this view, the collapse of quantum states within these structures could give rise to the subjective experience of consciousness, what it feels like to be you. But this theory is far from universally accepted. In fact, it's one of the most controversial ideas in neuroscience. Critics argue that the brain is too warm and noisy for delicate quantum processes to occur without being disrupted. They point out that quantum effects are typically observed in highly controlled environments like supercooled labs, not in the messy, bustling environment of the human brain. Despite these challenges, Penrose and Hameroff's theory continues to spark debate and inspire research, pushing scientists to explore the boundaries between physics, biology, and philosophy. The implications of quantum consciousness are profound. If true, it could mean that our minds are not just the sum of chemical reactions and electrical signals, but are deeply connected to the fundamental fabric of the universe. It could also challenge our understanding of free will, suggesting that our decisions might be influenced by quantum randomness rather than purely deterministic processes. And it raises questions about the nature of reality itself. Could consciousness be a fundamental feature of the universe, as some interpretations of quantum mechanics suggest? While the quantum consciousness theory remains speculative, it opens up exciting possibilities for understanding one of the greatest mysteries of all: the nature of our own awareness. As we continue to explore the quantum world, we might find that the key to unlocking the secrets of the mind lies in the strange and counterintuitive behavior of the smallest particles in existence. Next, we'll dive into another fascinating quantum phenomenon: the quantum vacuum and zero-point energy. What if empty space isn't really empty at all? Let's explore this intriguing idea. Now, let's turn our attention to something that might sound like a contradiction: empty space. But in the quantum world, nothing is ever truly empty. The quantum vacuum and zero-point energy reveal that what we perceive as empty is actually teeming with activity. At the smallest scales, space is filled with quantum fluctuations, tiny, unpredictable changes in energy that pop in and out of existence. These fluctuations are a direct consequence of Heisenberg's uncertainty principle, which tells us that even in a vacuum, energy cannot be precisely zero. Instead, there's always a baseline level of energy, known as zero-point energy, that permeates the fabric of the universe. This zero-point energy isn't just a theoretical curiosity. It has real implications for how we understand the cosmos. For one, it's thought to play a role in the expansion of the universe. Some theories suggest that the energy of the vacuum could be driving the accelerated expansion we observe, a phenomenon often attributed to dark energy. If true, this would mean that the seemingly empty space around us is actively shaping the fate of the universe on the largest scales. But the potential of zero-point energy doesn't stop there. Scientists have long wondered if this energy could be harnessed as a power source. Imagine tapping into the energy of the vacuum itself, a virtually limitless reservoir that exists everywhere, even in the void of space. While this idea remains speculative, it's a tantalizing possibility that could revolutionize energy production. However, the challenges are immense. Extracting usable energy from the quantum vacuum would require overcoming enormous technical hurdles, and for now, it remains a topic of theoretical exploration rather than practical application. The concept of zero-point energy also raises profound questions about the nature of reality. If empty space is filled with energy, does that mean the vacuum is alive with potential? Could these quantum fluctuations be the seeds of new particles or even new universes? Some theories suggest that the quantum vacuum might be the source of everything we see, with particles and forces emerging from its fluctuations. This idea blurs the line between nothingness and existence, challenging our understanding of what it means for something to be real. As we continue to explore the quantum vacuum, we're reminded that the universe is far stranger and more dynamic than it appears. What seems like empty space is actually a bustling arena of quantum activity, filled with energy and possibility. And while the practical applications of zero-point energy remain elusive, the very idea that we might one day harness the power of the vacuum is a testament to the boundless creativity of science. Next, we'll explore another intriguing quantum mystery: the idea that time itself might be quantized. Could time be made up of tiny, indivisible chunks? Let's find out. Now, let's shift our focus to something that might completely change how you think about time itself. What if time isn't the smooth, continuous flow we experience every day, but instead is made up of tiny, indivisible chunks? This is the essence of the quantum time hypothesis, a fascinating idea that suggests time might be quantized, much like energy or matter in the quantum world. Imagine time as a series of frames in a movie. Instead of flowing seamlessly, it moves forward in discrete steps like the ticking of a clock at the smallest possible scale. These ticks of time are thought to be the fundamental building blocks of reality, so tiny that they're far beyond our ability to perceive directly. But if this hypothesis is true, it could have profound implications for how we understand the universe. One of the most intriguing aspects of this idea is how it challenges our understanding of causality, the relationship between cause and effect. In a continuous flow of time, events happen in a clear sequence. One thing leads to another. But if time is quantized, there might be moments where cause and effect become blurred or even reversed. This could open the door to entirely new ways of thinking about the arrow of time, the direction in which time flows from past to future. Some theories even suggest that quantized time could allow for phenomena like time loops or microscopic time travel, where particles or information might briefly move backward in time. While these ideas are still speculative, they highlight just how strange and unpredictable the quantum world can be. The quantum time hypothesis also raises questions about the nature of reality itself. If time is made up of discrete chunks, does that mean the universe operates like a cosmic computer, processing information in tiny time steps? And if so, what does that say about the fundamental structure of existence? As we explore this idea, we're reminded once again that the quantum world is full of surprises. What seems like a simple, everyday concept, time, might actually be far more complex and mysterious than we ever imagined. And while the quantum time hypothesis is still a topic of intense debate and research, it offers a tantalizing glimpse into the deeper layers of reality. Next, we'll dive into another mind-bending quantum mystery, the challenge of reconciling quantum mechanics with gravity. How can these two fundamental forces of nature coexist? Let's find out. Now, let's turn our attention to one of the most perplexing puzzles in modern physics, the quantum gravity conundrum. At its core, this is the challenge of reconciling two of the most successful theories in science: quantum mechanics, which governs the behavior of the very small, and general relativity, which describes the force of gravity and the structure of the universe on the largest scales. While both theories work brilliantly in their own domains, they seem completely incompatible when brought together. Quantum mechanics tells us that particles and forces operate in a world of probabilities and uncertainties, where particles can exist in multiple states at once until observed. General relativity, on the other hand, paints a picture of a smooth, continuous spacetime that bends and warps in the presence of mass and energy. The problem arises when we try to apply quantum principles to gravity. Unlike the other fundamental forces, electromagnetism, the weak force, and the strong force, gravity resists being quantized. This has left scientists scratching their heads for decades, searching for a unified framework that can bridge the gap. One of the leading candidates to solve this conundrum is string theory. This ambitious idea proposes that the fundamental building blocks of the universe aren't point-like particles but tiny, vibrating strings. These strings can oscillate in different ways, giving rise to the various particles and forces we observe. String theory also suggests the existence of extra dimensions beyond the three spatial dimensions we're familiar with, which could help explain how gravity fits into the quantum world. While string theory is mathematically elegant, it has yet to be experimentally verified, leaving it in the realm of theoretical exploration. Another promising approach is loop quantum gravity. Unlike string theory, which tries to unify all forces, loop quantum gravity focuses specifically on quantizing spacetime itself. It imagines spacetime as a network of tiny, interconnected loops, creating a fabric that's granular at the smallest scales. This granularity could prevent the infinite densities that arise in classical black holes and the Big Bang, offering potential solutions to some of the most extreme puzzles in physics. However, like string theory, loop quantum gravity remains untested, and its mathematical complexity makes it a challenging field to advance. the quantum gravity conundrum isn't just an academic exercise, it's a quest to understand the very fabric of reality. Without a theory of quantum gravity, we can't fully explain phenomena like black holes, where quantum effects and gravity collide, or the conditions of the early universe, where quantum fluctuations may have seeded the structures we see today. It's a reminder that despite all we've learned, the universe still holds profound mysteries waiting to be unraveled. As we continue our journey through the quantum universe, we'll next explore how quantum systems lose their coherence and transition into the classical world we experience every day. This phenomenon, known as quantum decoherence, plays a crucial role in bridging the gap between the strange quantum realm and the familiar laws of physics. Let's dive in. Now, shifting our focus to the fascinating world of quantum decoherence, we uncover a process that helps explain why the strange, probabilistic nature of quantum mechanics gives way to the predictable, classical world we experience every day. Quantum decoherence is the phenomenon that causes quantum systems to lose their unique properties like superposition and entanglement and appear to behave like classical objects. But how does this happen? Let's break it down. At the heart of quantum decoherence is the idea of interaction. In the quantum realm, particles can exist in multiple states at once, a concept known as superposition. However, when these particles interact with their environment, whether it's through collisions with other particles or exposure to light, their delicate quantum states become entangled with the surroundings. This entanglement effectively leaks information about the quantum system into the environment, causing it to lose its coherence. Over time, this process makes the system appear to collapse into a single, definite state, aligning with the classical behavior we observe. This transition from quantum to classical isn't instantaneous. It depends on factors like the size of the system and the strength of its interactions with the environment. For example, a single electron in a vacuum might maintain its quantum properties for a long time, while a larger object like a dust particle would decohere almost instantly due to its constant interactions with air molecules and light. This explains why we don't see everyday objects in superposition. They're simply too entangled with their surroundings to maintain quantum coherence. Quantum decoherence also plays a critical role in resolving one of the biggest puzzles in quantum mechanics, the measurement problem. According to the Copenhagen interpretation, a quantum system remains in superposition until it's observed, at which point it collapses into a definite state. Decoherence provides a more nuanced explanation, suggesting that the act of measurement isn't what causes the collapse, it's the interaction with the environment that leads to the loss of coherence. This means that the classical world emerges naturally from the quantum world through these interactions, without the need for an external observer. But decoherence isn't just a theoretical curiosity, it has practical implications too. In the field of quantum computing, for instance, maintaining coherence is essential for performing complex calculations. Quantum bits or qubits rely on superposition and entanglement to process information, but they're highly susceptible to decoherence. Scientists are working tirelessly to isolate qubits from their environments to preserve their quantum states, a challenge that highlights the delicate balance between the quantum and classical worlds. As we reflect on quantum decoherence, it's clear that this phenomenon is a bridge between the bizarre quantum realm and the familiar classical universe. It helps us understand why the world at large scales behaves so differently from the world of atoms and particles, offering a glimpse into the intricate dance between quantum systems and their environments. Next, we'll explore another mind-bending quantum phenomenon, quantum tunneling, where particles defy classical physics by passing through barriers they seemingly shouldn't be able to overcome. Stay tuned as we uncover how this strange behavior shapes both the microscopic and macroscopic worlds. Now, let's venture into one of the most astonishing phenomena in quantum mechanics, quantum tunneling. Imagine a ball rolling up a hill. In the classical world, if the ball doesn't have enough energy to reach the top, it simply rolls back down. But in the quantum realm, particles don't always play by these rules. They can, in a sense, tunnel through barriers they seemingly shouldn't be able to overcome. This is quantum tunneling, and it's as strange as it sounds. At its core, quantum tunneling occurs because particles in the quantum world don't have definite positions or energies. Instead, they exist as probability waves, which describe the likelihood of finding a particle in a particular place. When a particle encounters a barrier, its probability wave doesn't abruptly stop at the barrier's edge. Instead, it extends into and even beyond the barrier, meaning there's a small but real chance the particle can appear on the other side, as if it had tunneled through. This isn't just theoretical, it's been observed in countless experiments and is a cornerstone of modern physics. One of the most fascinating applications of quantum tunneling is in electronics. The tunnel diode, for example, relies on this phenomenon to allow electrons to pass through a thin barrier, enabling faster switching speeds than traditional diodes. This principle is also at the heart of scanning tunneling microscopes, which use tunneling currents to create incredibly detailed images of surfaces at the atomic level. Without quantum tunneling, much of the technology we take for granted today, from advanced medical imaging to cutting-edge semiconductor devices, simply wouldn't exist. But the implications of quantum tunneling go far beyond technology. It challenges our understanding of reality itself. If particles can appear on the other side of a barrier without ever physically crossing it, what does that say about the nature of space and time? Some scientists have even speculated that quantum tunneling could play a role in processes like nuclear fusion in stars, where particles overcome immense energy barriers to fuse together, releasing the energy that powers the universe. Quantum tunneling also raises profound questions about determinism. In classical physics, if you know a particle's energy and the height of a barrier, you can predict with certainty whether it will pass through. But in the quantum world, tunneling introduces an element of unpredictability. A particle might tunnel through a barrier one moment and fail the next, governed only by probabilities. This inherent randomness is a hallmark of quantum mechanics and a reminder that the universe operates in ways that often defy our intuition. As we wrap up our exploration of quantum tunneling, it's clear that this phenomenon is more than just a scientific curiosity. It's a window into the deeper workings of reality. From enabling groundbreaking technologies to challenging our fundamental understanding of physics, quantum tunneling continues to inspire and perplex scientists and thinkers alike. Next, we'll dive into the framework of quantum field theory, where particles are seen as excitations of underlying fields. Stay with us as we uncover how this powerful idea shapes our understanding of the universe. Now, shifting our focus to a cornerstone of modern physics, let's explore the quantum field theory framework. This theory takes the strange and fascinating world of quantum mechanics and expands it into an even more profound understanding of the universe. At its heart, quantum field theory proposes that particles aren't just tiny, isolated objects, they're excitations or ripples in underlying fields that permeate all of space and time. Think of these fields as invisible oceans and particles as the waves that rise and fall on their surface. This idea has revolutionized how we think about matter, energy, and the forces that govern them. Quantum field theory has been remarkably successful in explaining the fundamental forces of nature. Take electromagnetism, for example. In this framework, the electromagnetic force isn't just a mysterious interaction between charged particles. It's mediated by photons, which are excitations of the electromagnetic field. Similarly, the strong nuclear force, which holds atomic nuclei together, is carried by particles called gluons arising from the strong force field. Even the weak nuclear force, responsible for processes like radioactive decay, is explained through the exchange of particles like W and Z bosons. This unified approach has allowed physicists to describe 3 of the 4 fundamental forces within a single theoretical framework. But quantum field theory doesn't stop there. It also provides a deeper understanding of particles themselves. In this view, particles like electrons, quarks, and neutrinos aren't just isolated entities, they're manifestations of their respective quantum fields. An electron, for instance, is an excitation of the electron field. This perspective not only simplifies our understanding of particles, but also helps explain phenomena like particle creation and annihilation. When an electron and a positron collide and produce photons, it's not just a random event, it's a transformation of excitations in the electron and positron fields into excitations in the electromagnetic field. One of the most remarkable achievements of quantum field theory is its ability to predict and explain the behavior of particles with incredible precision. The development of quantum electrodynamics, or QED, which describes how light and matter interact, is a shining example. QED's predictions have been confirmed to an astonishing degree of accuracy, making it one of the most successful theories in the history of science. Similarly, the Standard Model of particle physics, built on the foundation of quantum field theory, has successfully predicted the existence of particles like the Higgs boson, which was discovered in 2012. Yet, despite its successes, quantum field theory isn't without its challenges. For one, it doesn't yet incorporate gravity, the 4th fundamental force. While quantum field theory excels at describing the other 3 forces, gravity remains the domain of general relativity, and reconciling the two remains one of the greatest unsolved problems in physics. Additionally, the mathematics of quantum field theory can become incredibly complex, especially when dealing with phenomena like quantum chromodynamics, which describes the strong force. These complexities remind us that while quantum field theory is a powerful tool, it's still a work in progress. As we reflect on the quantum field theory framework, it's clear that this idea has fundamentally reshaped our understanding of the universe. By viewing particles as excitations of underlying fields, we gain a deeper appreciation for the interconnectedness of all things. From explaining the forces that bind atoms to predicting the existence of new particles, quantum field theory continues to be a driving force in modern physics. Next, we'll turn our attention to the concept of quantum supremacy, where quantum computers might solve problems beyond the reach of classical machines. Stay with us as we explore how this emerging technology could redefine the limits of computation. Now, stepping into the realm of cutting-edge technology, let's dive into the concept of quantum supremacy. This idea revolves around the potential for quantum computers to tackle problems that are simply out of reach for classical computers. Unlike traditional computers, which rely on bits that can be either 0 or 1, quantum computers use qubits. These qubits can exist in a state of superposition, meaning they can be both 0 and 1 simultaneously. This unique property allows quantum computers to process vast amounts of information in parallel, opening up possibilities that were once thought impossible. One of the most exciting implications of quantum supremacy lies in the field of cryptography. Classical encryption methods, which secure everything from online banking to confidential communications, rely on the difficulty of solving complex mathematical problems. For example, factoring large numbers into primes is a task that would take classical computers an impractical amount of time. However, quantum computers, with their ability to perform multiple calculations at once, could crack these codes in a fraction of the time. This has sparked a race to develop quantum-resistant encryption methods, ensuring that our digital world remains secure even as quantum technology advances. But cryptography isn't the only area where quantum supremacy could make waves. Artificial intelligence, or AI, stands to benefit significantly from this breakthrough. Machine learning algorithms, which power everything from voice assistants to self-driving cars, often require massive amounts of computational power to process and analyze data. Quantum computers could accelerate these processes exponentially, enabling AI systems to learn faster, make more accurate predictions, and solve problems that are currently too complex for classical systems. Imagine AI models that can simulate entire ecosystems, optimize global supply chains, or even design new medicines with unprecedented precision, all thanks to the power of quantum computing. Of course, achieving quantum supremacy isn't without its challenges. Building and maintaining stable quantum systems is incredibly difficult, as qubits are highly sensitive to their environment. Even the slightest interference can cause errors, a problem known as quantum decoherence. Researchers are working tirelessly to develop error-correcting codes and more robust qubit designs, but these hurdles remind us that quantum supremacy is still in its early stages. Despite these challenges, the progress made so far is nothing short of remarkable. As we look to the future, the concept of quantum supremacy holds immense promise. From revolutionizing cryptography to supercharging artificial intelligence, the potential applications are vast and transformative. While we may not yet have fully functional quantum computers solving real-world problems at scale, the groundwork being laid today could pave the way for a new era of technological innovation. Next, we'll explore the intriguing hypothesis of quantum Darwinism, which suggests that classical reality emerges from quantum systems through a process akin to natural selection. Stay tuned as we unravel how this idea bridges the gap between the quantum and classical worlds. Now, shifting our focus to a fascinating intersection of quantum mechanics and evolutionary theory, let's explore the quantum Darwinism hypothesis. This theory proposes that classical reality, the stable, predictable world we experience, emerges from the chaotic quantum realm through a process similar to natural selection. Just as species evolve over time to adapt to their environment, certain quantum states become selected and amplified while others fade away. This process ensures that the information about these states is widely distributed and accessible, creating the consistent reality we observe. At the heart of quantum Darwinism is the idea of environmental selection. In the quantum world, particles exist in superpositions, meaning they can be in multiple states at once. However, when these particles interact with their surroundings like air molecules, light, or other particles, only certain states survive these interactions. These surviving states are the ones that can be repeatedly observed and measured, effectively becoming the building blocks of classical reality. It's as if the environment acts as a filter, favoring states that are robust enough to persist and be shared across multiple observers. This hypothesis has profound implications for the observer effect, a cornerstone of quantum mechanics. The observer effect suggests that the act of measurement collapses a quantum system into a definite state. Quantum Darwinism offers a fresh perspective, proposing that it's not just the observer but the environment itself that plays a crucial role in this process. The environment continuously measures quantum systems, selecting states that are stable and reproducible. This means that what we perceive as reality is essentially a consensus formed by countless interactions between quantum systems and their surroundings. One of the most intriguing aspects of quantum Darwinism is how it bridges the gap between the quantum and classical worlds. It provides a mechanism for how the strange, probabilistic nature of quantum mechanics gives rise to the deterministic laws of classical physics. This theory also suggests that the universe has a built-in way of ensuring consistency, making it possible for multiple observers to agree on the same reality. Without this process, the quantum world would remain a chaotic, unpredictable mess, and the classical world as we know it might never have emerged. As we ponder the implications of quantum Darwinism, it's worth considering how this theory reshapes our understanding of observation and reality. It challenges the notion that observers are the sole arbiters of quantum states, instead highlighting the role of the environment in shaping what we perceive. This idea not only deepens our appreciation for the complexity of the quantum world, but also offers a new lens through which to view the nature of existence itself. Next, we'll delve into the quantum entropy paradox, a puzzling phenomenon that questions how quantum systems might defy the second law of thermodynamics. Stay with us as we uncover how this paradox could reshape our understanding of time and the universe's ultimate fate. Now, let's turn our attention to a puzzling question that challenges one of the most fundamental laws of physics, the quantum entropy paradox. At its core, this paradox explores how quantum systems might behave in ways that seem to defy the second law of thermodynamics, a principle that governs the flow of energy and the inevitable increase of entropy or disorder in the universe. According to this law, entropy always increases in isolated systems, leading to the eventual heat death of the universe, a state where all energy is evenly distributed and no work can be done. But what if quantum mechanics offers a way to bend or even break this rule? In the quantum realm, particles don't always follow the predictable paths we see in classical physics. Instead, they exist in superpositions where multiple states coexist until measured. This inherent unpredictability opens the door to phenomena that seem to reverse or halt the increase of entropy, at least temporarily. For example, quantum tunneling allows particles to pass through barriers that would be insurmountable in classical physics, effectively reducing entropy in localized systems. Similarly, quantum entanglement, where particles remain connected across vast distances, can create correlations that appear to lower entropy in certain scenarios. These behaviors suggest that, on a quantum level, the arrow of time might not be as rigid as we once thought. The implications of this paradox are profound. If quantum systems can temporarily reduce entropy, it raises questions about the inevitability of the universe's heat death. Could quantum mechanics provide a loophole, allowing pockets of order to persist even as the universe as a whole trends toward disorder? Some researchers speculate that quantum processes might play a role in sustaining complexity, potentially offering a way to delay or mitigate the effects of entropy on cosmic scales. This idea not only challenges our understanding of thermodynamics, but also invites us to rethink the nature of time itself. Is time truly irreversible, or could quantum effects create conditions where entropy decreases, even if only for brief moments? One of the most intriguing aspects of the quantum entropy paradox is its connection to the arrow of time. In classical physics, the arrow of time points in one direction, toward increasing entropy and disorder. But quantum mechanics introduces the possibility of fluctuations that could momentarily reverse this trend. These fluctuations might be rare and short-lived, but they hint at a universe where the rules of thermodynamics are not as absolute as they seem. This raises the tantalizing question: could life, or even the universe itself, exploit these quantum quirks to sustain order in the face of entropy? As we explore this paradox, it's worth considering how it might reshape our understanding of the universe's ultimate fate. While the heat death of the universe remains a widely accepted scenario, the quantum entropy paradox suggests that the story might not be so straightforward. Quantum mechanics introduces a layer of complexity that could allow for pockets of order to emerge, even in a universe dominated by entropy. This idea not only deepens our appreciation for the strange and counterintuitive nature of quantum physics, but also offers a glimmer of hope that the universe's story might be far more dynamic and unpredictable than we ever imagined. Next, we'll venture into the realm of spacetime itself, as we explore the quantum wormhole hypothesis, a theory that suggests entangled particles might be connected by microscopic wormholes. Stay with us as we uncover how this idea could revolutionize our understanding of quantum gravity and the fabric of reality. Now, shifting our focus to the fabric of spacetime itself, let's explore the quantum wormhole hypothesis, a theory that takes the strange phenomenon of quantum entanglement and ties it to the very structure of the universe. At its heart, this hypothesis suggests that entangled particles, those mysterious partners that remain connected across vast distances, might be linked by microscopic wormholes. These wormholes, often imagined as tunnels through space-time, could provide a physical explanation for how particles can instantaneously influence each other, no matter how far apart they are. To understand this idea, let's revisit quantum entanglement. When two particles become entangled, measuring one instantly determines the state of the other, even if they're light years apart. This spooky action at a distance, as Einstein famously called it, defies our classical understanding of space and time. The quantum wormhole hypothesis proposes that this connection isn't just a mathematical quirk but a physical bridge, a tiny wormhole threading through the fabric of space-time. In this view, entanglement isn't just a correlation, it's a literal connection, a shortcut through the universe's geometry. This idea has profound implications for our understanding of quantum gravity, the long-sought theory that aims to unify quantum mechanics with general relativity. Wormholes, originally predicted by Einstein's equations, are typically thought of as massive structures requiring enormous amounts of energy to sustain. But the quantum wormhole hypothesis suggests that these bridges might exist on a much smaller scale, woven into the quantum fabric of reality. If true, it could mean that space-time itself is fundamentally interconnected, with wormholes acting as the glue that binds entangled particles together. One of the most exciting aspects of this hypothesis is its potential to resolve some of the deepest mysteries in physics. For instance, it could shed light on the black hole information paradox, the question of whether information swallowed by a black hole is truly lost. If wormholes connect entangled particles, they might also provide a way for information to escape black holes, preserving the laws of quantum mechanics. Additionally, this idea could offer new insights into the nature of space-time, suggesting that it's not a smooth, continuous fabric but a network of microscopic connections. While the quantum wormhole hypothesis is still speculative, it represents a bold step toward reconciling quantum mechanics with gravity. It challenges us to rethink the very nature of reality, suggesting that the universe might be far more interconnected than we ever imagined. As we continue to explore this idea, we're reminded that the quantum realm is full of surprises, constantly pushing the boundaries of what we thought was possible. Next, we'll delve into one of the most perplexing questions in quantum physics, the quantum measurement problem. What happens when a quantum system transitions from a superposition of states to a single, definite outcome? Join us as we unravel this mystery and its implications for the nature of reality. Now, let's turn our attention to one of the most puzzling questions in quantum physics, the quantum measurement problem. This mystery lies at the heart of how we understand the transition from the strange, probabilistic world of quantum mechanics to the definite, concrete reality we experience every day. At its core, the problem asks, how does a quantum system which can exist in multiple states at once, a phenomenon known as superposition, suddenly collapse into a single, measurable outcome when observed? To grasp this, let's start with superposition. In the quantum realm, particles like electrons or photons don't have definite properties until they're measured. Instead, they exist in a blend of all possible states. For example, an electron might be in a superposition of spinning both clockwise and counterclockwise at the same time. But the moment we measure it, it chooses one state. The question is, what causes this collapse and why does observation play such a crucial role? The Copenhagen interpretation, one of the earliest and most widely taught explanations, suggests that the act of measurement itself forces the quantum system to settle into a definite state. According to this view, the observer is inseparable from the system being observed. In other words, reality doesn't exist in a concrete form until it's measured. This idea places consciousness or observation at the center of quantum mechanics, a notion that has sparked both fascination and debate. On the other hand, the many worlds interpretation offers a radically different perspective. Instead of a single outcome, it proposes that every possible outcome of a quantum measurement actually happens, but in separate, branching universes. In this view, there's no collapse of the wave function. Instead, the universe splits into multiple realities, each corresponding to a different measurement result. So, if an electron can spin clockwise or counterclockwise, both outcomes occur but in parallel worlds. This interpretation eliminates the need for an observer to collapse the system, but it introduces the mind-bending idea of an infinite multiverse. Both interpretations have their strengths and challenges. The Copenhagen interpretation aligns with our intuitive understanding of measurement, but leaves the role of the observer somewhat mysterious. The many worlds interpretation avoids the collapse problem, but requires us to accept the existence of countless parallel universes. Neither provides a complete answer, and the quantum measurement problem remains one of the most hotly debated topics in physics. This unresolved question has profound implications for our understanding of reality. It forces us to confront the limits of our knowledge and the nature of observation itself. Are we, as observers, shaping reality, or are we merely one thread in an infinite tapestry of parallel worlds? As we continue to explore this mystery, we're reminded that the quantum world is far stranger and more interconnected than we ever imagined. Next, we'll dive into the quantum cosmology framework, exploring how quantum mechanics might describe the origins of the universe itself. How did the Big Bang unfold in the quantum realm? Stay with us as we uncover the secrets of the cosmos. Now, let's shift our focus to the quantum cosmology framework, a fascinating approach that applies the principles of quantum mechanics to the very beginning of the universe. This theory seeks to answer one of the most profound questions in science: how did the universe emerge from nothingness? By exploring the quantum realm, we might uncover clues about the origins of the Big Bang and the potential existence of a multiverse. At the heart of quantum cosmology is the idea that the early universe was governed by quantum laws, just like the particles and forces we study today. In this framework, the universe didn't start as a single, infinitely dense point, as classical Big Bang theory suggests. Instead, it may have begun as a quantum fluctuation, a tiny, random event in the fabric of spacetime. This fluctuation could have triggered the expansion we now observe, setting the stage for everything that exists. One of the key concepts in quantum cosmology is the wave function of the universe. Just as particles exist in superpositions of states, the entire universe might have started in a superposition of possible configurations. Over time, this wave function could have collapsed into the specific universe we inhabit today. But here's where it gets even more intriguing. Some interpretations suggest that other universes with different physical laws and constants might have also emerged from this quantum process. This idea ties quantum cosmology directly to the multiverse hypothesis, proposing that our universe is just one of countless others. The implications of this framework are staggering. If the Big Bang was a quantum event, it means the universe's birth was inherently probabilistic, not deterministic. There was no single, inevitable outcome, just a range of possibilities. This challenges our classical understanding of cause and effect, suggesting that the universe's existence might be the result of chance rather than necessity. Moreover, quantum cosmology raises questions about the nature of time itself. In the early universe, time as we know it might not have existed. Instead, time could have emerged as the universe expanded and cooled, transitioning from a quantum state to a classical one. This idea blurs the line between the quantum and classical worlds, hinting at a deeper connection between the two. As we explore the quantum cosmology framework, we're reminded that the universe's origins are still shrouded in mystery. While this theory offers a compelling way to understand the Big Bang and the multiverse, it also highlights the limits of our current knowledge. What caused the initial quantum fluctuation? Why did our universe emerge with the specific laws and constants we observe? These questions push the boundaries of physics and philosophy, inviting us to rethink our place in the cosmos. Next, we'll delve into the quantum chaos theory, examining how even the smallest quantum systems can exhibit unpredictable, chaotic behavior. How does this chaos shape the universe at its most fundamental level? Stay tuned as we unravel the mysteries of quantum unpredictability. Now, let's step into the fascinating world of quantum chaos theory, where the unpredictable nature of quantum systems takes center stage. At first glance, chaos might seem like the opposite of what we expect from the precise and mathematical world of quantum mechanics. But here's the twist. Even in the quantum realm, chaos plays a crucial role, shaping the behavior of particles and systems in ways that defy our classical intuition. Quantum chaos explores how tiny quantum systems can exhibit chaotic behavior, much like the way a butterfly flapping its wings can set off a chain reaction leading to a storm on the other side of the world. In classical physics, chaos refers to systems that are highly sensitive to initial conditions, making their long-term behavior unpredictable. But in the quantum world, chaos takes on a different flavor. Instead of trajectories becoming unpredictable, it's the wave functions, the mathematical descriptions of quantum states, that become complex and tangled. One of the key features of quantum chaos is the way energy levels in a system are distributed. In a chaotic quantum system, these energy levels don't follow a regular pattern. Instead, they appear random, much like the way raindrops scatter across a windshield. This randomness isn't just a quirk, it's a fundamental property of chaotic quantum systems, and it has profound implications for how we understand the universe. For example, consider the behavior of electrons in an atom. In a non-chaotic system, electrons move in predictable orbits like planets around a star. But in a chaotic quantum system, their behavior becomes erratic, making it nearly impossible to predict their exact positions or energies. This unpredictability isn't just a limitation of our tools or knowledge, it's a fundamental aspect of the system itself. The implications of quantum chaos extend far beyond the microscopic world. It challenges our understanding of predictability and determinism, suggesting that even in the quantum realm, there are limits to how much we can know about the future. This idea resonates with the famous Heisenberg uncertainty principle, which states that we can't simultaneously know both the position and momentum of a particle with absolute precision. Quantum chaos takes this a step further, showing that even when we have all the information we can possibly gather, some systems remain inherently unpredictable. But quantum chaos isn't just about unpredictability, it also offers insights into the nature of reality itself. Some researchers believe that chaotic quantum systems might hold the key to understanding how classical physics emerges from the quantum world. In other words, the chaos we observe in quantum systems could be the bridge between the strange, probabilistic nature of the quantum realm and the familiar, deterministic laws of classical physics. As we explore quantum chaos theory, we're reminded that the universe is far more complex and mysterious than we often assume. It's a place where order and disorder coexist, where predictability and randomness are two sides of the same coin. This theory invites us to rethink our assumptions about the nature of reality, challenging us to embrace the chaos as an essential part of the cosmic tapestry. Next, we'll turn our attention to the intriguing connection between quantum entanglement and time, where particles seem to defy our classical understanding of cause and effect. How can entangled particles influence each other across time? Stay with us as we unravel this mind-bending phenomenon. Now, let's venture into the mind-bending realm of quantum entanglement and time, where the rules of cause and effect seem to blur in ways that challenge our deepest intuitions. Imagine two particles separated by vast distances, yet so deeply connected that what happens to one instantly affects the other. This phenomenon, known as quantum entanglement, has long puzzled scientists. But what if this connection isn't just spatial? What if it also defies our understanding of time itself? In classical physics, time flows in one direction from past to future, and events are bound by cause and effect. But in the quantum world, entangled particles appear to communicate instantaneously, regardless of the distance between them. This raises a startling question. Could entanglement also transcend time? Could particles influence each other not just across space, but across moments in time? Recent experiments have begun to explore this possibility, pushing the boundaries of what we thought was possible. One groundbreaking study involved creating entangled particles and then measuring one particle before the other, effectively testing whether the measurement of the first particle could influence the state of the second particle retroactively. The results were astonishing. The measurements suggested that the entangled particles seemed to know about each other's states even when the measurements were made at different times, as if the influence traveled backward through time. This idea challenges the very foundation of our understanding of time. If entangled particles can influence each other across time, does that mean the future can affect the past? Or is time itself more fluid and interconnected than we've ever imagined? These questions don't just belong to the realm of science fiction. They're at the forefront of cutting-edge quantum research. One interpretation of these findings is that time, as we experience it, might not be as linear as we think. Instead, it could be more like a web of interconnected moments where past, present, and future are all intertwined. This perspective aligns with some theories in quantum mechanics that suggest time might not be a fundamental feature of the universe, but rather an emergent property arising from deeper quantum processes. The implications of this are profound. If time isn't as rigid as we've always believed, it could reshape our understanding of everything from the origins of the universe to the nature of consciousness. It also raises philosophical questions about free will and determinism. If the future can influence the past, does that mean our choices are predetermined, or is there still room for genuine agency? As we continue to explore the mysteries of quantum entanglement and time, we're reminded that the universe is far stranger and more interconnected than we've ever imagined. It's a place where the boundaries between space and time dissolve, where the past, present, and future might all be part of a single, unified tapestry. This theory invites us to rethink not just our understanding of physics, but our very perception of reality itself. Next, we'll dive into the fascinating world of quantum information theory, where information itself becomes the fundamental building block of the universe. What does it mean for reality to be made of information? Stay with us as we uncover this groundbreaking idea. Now, let's shift our focus to a theory that redefines the very fabric of reality: quantum information theory. At its core, this idea suggests that information is not just a byproduct of the universe, but its fundamental building block. Imagine the universe as a vast, intricate network of data, where every particle, every interaction, and every event is encoded in a cosmic language of information. This perspective challenges our traditional view of matter and energy, proposing that what we perceive as physical reality might actually be a manifestation of underlying information. One of the most striking implications of quantum information theory lies in the study of black holes. According to this framework, black holes are not just gravitational monsters but also information processors. When matter falls into a black hole, it doesn't simply disappear, it's transformed into information encoded on the black hole's event horizon, a concept known as the holographic principle. This idea suggests that the information about everything that enters a black hole is preserved, even if it's scrambled beyond recognition. This has profound implications for our understanding of space, time, and the conservation of information in the universe. Quantum computing is another area where this theory takes center stage. Unlike classical computers, which process information in binary bits, quantum computers use qubits, particles that can exist in multiple states simultaneously. This allows them to perform complex calculations at speeds unimaginable to traditional systems. Quantum information theory underpins this technology, providing the framework for how information is stored, processed, and transmitted in the quantum realm. It's not just about faster computers, it's about unlocking entirely new ways of solving problems, from simulating molecular interactions to cracking encryption codes. But perhaps the most mind-bending aspect of quantum information theory is its implications for the nature of reality itself. If information is fundamental, then what we perceive as the physical world might be akin to a projection or simulation, emerging from a deeper layer of informational processes. This idea resonates with the simulation hypothesis, suggesting that our universe could be a vast computational system. It also raises questions about the nature of consciousness and observation. Could our awareness itself be a form of information processing? As we explore quantum information theory, we're invited to rethink not just the mechanics of the universe, but the very essence of existence. It's a theory that bridges the gap between the abstract and the tangible, offering a new lens through which to view everything from the smallest particles to the largest cosmic structures. And as we continue to unravel its mysteries, we may find that the universe is not just a collection of objects and forces, but a symphony of information waiting to be decoded. Next, we'll explore the final frontier of our journey, the idea that the universe itself might be a quantum computer. What does it mean for reality to be a computation? Stay with us as we dive into this groundbreaking concept. Now, let's take a step into one of the most fascinating and speculative ideas in modern physics, the notion that the universe itself might function as a quantum computer. This theory suggests that the cosmos isn't just governed by the laws of physics, but is, in essence, a vast computational system, processing information at every level of existence. It's a concept that blurs the line between science and philosophy, challenging us to rethink what reality truly is. At the heart of this idea is the principle that the universe operates like a quantum computer, where every particle, every interaction, and every event is part of an immense computational process. Just as a quantum computer uses qubits to perform calculations, the universe might use the fundamental building blocks of reality, particles and fields, to process information. This perspective shifts our understanding of the cosmos from a collection of physical objects to a dynamic, information-driven system. One of the most intriguing implications of this theory is its connection to the simulation hypothesis. If the universe is a quantum computer, then it's possible that what we perceive as reality is the output of a cosmic computation. This idea suggests that the physical world we experience could be akin to a simulation, generated by the underlying informational processes of the universe. It's a thought that echoes the age-old question, are we living in a simulated reality? While this might sound like science fiction, it's a question that physicists and philosophers are taking increasingly seriously. The quantum universe as a quantum computer also has profound implications for the nature of time and causality. In a computational framework, time could be seen as a sequence of computational steps, with each moment representing a new state in the universe's ongoing calculation. This challenges our traditional view of time as a continuous flow, suggesting instead that it might be quantized, broken into discrete units, much like the frames of a film. This idea aligns with theories in quantum gravity, which propose that spacetime itself might be granular at the smallest scales. Another fascinating aspect of this theory is its potential to unify the fundamental forces of nature. If the universe is a quantum computer, then the laws of physics could be seen as the algorithms that govern its operations. This perspective offers a new way to approach the unification of quantum mechanics and general relativity, two frameworks that have so far resisted integration. By viewing the universe as a computational system, physicists might find a common language to describe both the quantum and cosmic realms. But what does this mean for us as observers within this vast quantum computer? If the universe is processing information, then our consciousness and perception could be part of that computational process. This raises profound questions about the nature of awareness and free will. Are we active participants in the universe's computation, or are we merely outputs of its algorithms? These questions push the boundaries of both science and philosophy, inviting us to explore the deepest mysteries of existence. As we wrap up our exploration of the quantum universe as a quantum computer, we're left with a sense of awe and wonder. This theory doesn't just challenge our understanding of reality, it redefines it, offering a new lens through which to view the cosmos. Whether the universe is a quantum computer, a simulation, or something even more profound, one thing is clear: the nature of reality is far stranger and more complex than we ever imagined. And as we continue to probe these mysteries, we may find that the answers lie not in the stars, but in the very fabric of information that weaves the universe together. As we bring our journey through these 30 mind-bending theories to a close, it's impossible not to feel a sense of awe at the sheer complexity and wonder of the quantum universe. From the many worlds interpretation to the idea of the universe as a quantum computer, each theory challenges our understanding of reality in profound and unexpected ways. Together, they paint a picture of a cosmos that is far stranger, more interconnected, and more mysterious than we ever imagined. These theories don't just expand our knowledge, they redefine it. They push us to question the very nature of existence, from the smallest particles to the vastness of spacetime. Whether it's the idea that every decision spawns a new universe, or the possibility that our reality is a holographic projection, these concepts force us to confront the limits of human understanding. They remind us that the universe is not just a collection of objects and forces, but a dynamic, ever-evolving system that operates on principles we are only beginning to grasp. But perhaps the most exciting aspect of these theories is what they leave unanswered. Each one opens new doors, inviting us to explore deeper into the unknown. They challenge us to think beyond the familiar, to imagine possibilities that stretch the boundaries of science and philosophy. And in doing so, they remind us that the pursuit of knowledge is not just about finding answers, it's about asking better questions. So, what do you think? Do these theories resonate with your own ideas about the universe, or do they leave you with even more questions than before? The beauty of science is that it's a conversation, one that evolves with every new discovery and every new perspective. We'd love to hear your thoughts in the comments below. Which theory fascinates you the most? Are there any you think we missed? Let's keep the discussion going. And if you're as captivated by these ideas as we are, don't forget to like, subscribe, and hit the notification bell so you never miss a journey into the mysteries of the cosmos. The universe is full of wonders waiting to be uncovered, and we're just getting started. Thanks for joining us on this exploration. Until next time, keep questioning, keep exploring, and keep wondering about the incredible world we live in.